Having looked into the mechanism of hemiacetal hydrolysis, we can now turn our attention to acetal hydrolysis. So, reaction of an acetal with water under acidic conditions only results in hydrolysis of the acetal to generate a molecule of aldehyde or ketone and 2 molecules of alcohol. Okay, so an example is given below with acetone dimethyl acetal reacting with H3O+ to get 1 molecule of acetone and 2 molecules of methanol. And the mechanism of this is the exact reverse of acetal formation, and in many ways is very similar to the mechanism we looked at in the previous video of hemiacetal hydrolysis under acidic conditions. So the first step is protonation of an ether oxygen. There are 2 ether oxygens. Which one do you choose? Doesn't make any difference. I chose the left one. You could choose the right one. So it gets protonated with aqueous acid, H3O+, to make a good leaving group. And then in the second step, that leaving group is going to leave, so we lose the neutral alcohol as our leaving group to form an oxocarbocation. Remember that the oxocarbocation has another resonance structure with the plus charge on the oxygen. Moving forward through the mechanism, you can work from either resonance structure, but I find it more convenient at this point to work from the resonance structure with the plus charge on carbon. Because the next step of the mechanism is the attack of water, not H3O+, but H2O, as a nucleophile on the oxocarbocation. This forms an oxygen-carbon bond. The oxygen that is coming in now as water is actually going to end up being the carbonyl oxygen once we are done with the mechanism. So the oxygen comes in, attacks the carbon, and if the oxygen is a neutral nucleophile, the immediate intermediate that you get after nucleophilic attack has a positive charge on the oxygen. Now, the next thing that has to happen is we have to transfer one of those hydrogens on the oxygen that just came in to the other ether oxygen to make the ether oxygen into a leaving group and allow another molecule of neutral alcohol to leave. Okay, you can do this proton transfer intermolecularly, meaning you can transfer it to a molecule of H2O, and then from that molecule of H2O, of H3O+ that you have generated to the ether oxygen. I prefer to do this proton transfer intramolecularly. In one step, I send that proton directly over to the ether oxygen. Of course, when you draw this with arrows, you have to have an arrow coming from the ether oxygen to the hydrogen on the cationic oxygen. So that forms the new oxygen-hydrogen bond, and then you need a second arrow to cleave the oxygen-hydrogen bond. So now we're in the situation where we have a neutral alcohol group and a protonated ether group, and we are exactly in the same place we were after the first protonation in the acidic hemiacetal hydrolysis mechanism. So from here on, you have seen it all. Step 5 is loss of the neutral alcohol as a leaving group to form an oxocarbocation. And now we will work from the resonance structure that is the protonated carbonyl. So step 6 now will be deprotonation of the cationic oxygen using water as the base to yield the neutral ketone. Okay, so the 2 methanols were kicked off in step 2 and then in step 5. And then finally we have lost the 2 hydrogens that were originally on the waters in step 4 and step 6. So every step of this mechanism does something to get us closer to the final products that we want. It's a 6-step mechanism. It is a longer mechanism than most of the ones you have seen up until this point, but these steps should all make sense. Again, many of these steps are proton transfer reactions that set up the key steps of nucleophilic attack and leaving group leaving. Now, just as a final note on this reaction, I said that this has to happen under acidic conditions only. There is no basic mechanism for acetal hydrolysis because the first step of the basic mechanism for hemiacetal hydrolysis is deprotonation of the OH on the hemiacetal. But since acetals do not have an OH, there is nothing to deprotonate. So as a result, acetals are completely stable under basic conditions. Hemiacetals are much easier to hydrolyze because they can hydrolyze under either acidic or basic conditions. An acetal will stay on indefinitely as long as the solution is neutral or at all basic. It is essentially only under strongly acidic conditions that acetals hydrolyze. Okay, so this ends our discussion of the addition of oxygen functional groups to carbonyls. We looked at hemiacetal formation and hydrolysis, and we looked at acetal formation and hydrolysis. In the next set of videos, we will shift gears and start talking about the addition of nitrogen nucleophiles to aldehydes and ketones.